In this video, we discuss learning outcome number 6 of lesson 8.1, which is about the power of a hypothesis test. And we're going to focus on this qualitatively. We're going to talk about what it is and some of the variables that affect the power of a hypothesis test, but we're not actually going to do any computation. We're going to discuss interpreting power of a hypothesis test and what it is used for. So here's the definition. The power of a hypothesis test is the probability, 1 minus beta, of rejecting a false null hypothesis. So the null is false and we're rejecting it. We're saying, what is that power? Now, the value of the power is computed using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed to be true in the null hypothesis. So let's say that the null hypothesis says that the population parameter is equal to 0.2. Well, you would have to, in order to compute the power of a hypothesis test, you would have to see what the power would be provided that the population parameter weren't 0.2, but it was 0.3 instead, or 0.4 instead, or 0.5 instead. So this power of a hypothesis test requires us to have some comparison value for that population parameter. Now, for a given sample size and effect size is related to variance, the lower the alpha, and again, that's the probability of a type 1 error, the higher the beta will be. That's the probability of a type 2 error. And I see a little mistake here. It needs to be apparent there. There we go. Okay. Now, I just read about this at this link. I think the website is called realstatistics.com or something like that. But if you follow this hyperlink, you can learn a little bit more about power. It's again explained qualitatively in our textbook, and technology will allow you to find power even without being able to compute beta directly. So let's look at an example. Let's say that there were 13 girls among 14 babies born to couples using the X-sort method, which is supposed to make it more likely that you have a girl. So if you have 13 girls out of 14 babies, that's a lot of girls. So you might think that the X-sort method is working. If we want to test the claim that the girls are more likely, so that the probability is greater than 0.5 using this method, we'll have the following null and alternative hypotheses. So the alternative would be that P is greater than 0.5, and the null would be that P is equal to 0.5, or the probability of having a girl using this method is exactly 50%, 50-50, just like you would typically expect. Somebody's having a child, you expect 50% chance of getting a boy and a 50% chance of getting a girl approximately. Now, if we use a significance level of alpha equals 0.05, in order to find power, we need comparison values of the population parameter P as an alternative to the proposed value in the null hypothesis. So we're saying that that population proportion, is 0.5. But we're now, in order to compute power, we need to know, well, what's the difference between that 0.5 and another true population proportion? Maybe 0.5 is wrong. Let's compare that population proportion of 0.5 to possible population proportions of 0.6 and 0.7 and 0.8 and 0.9. For each of those, we can compute the power. Now, this output on this next table here was computed using a program called Minitab, and they are using exact calculations rather than a normal distribution or a normal approximation to a binomial distribution here. So for these values of P, we get these values of beta. That is the probability of a type 2 error. And then the power of the test is 1 minus beta. So that's if beta is 0.82, the power of the test is 0.18. Our goal is not to be able to come up with these numbers, but to be able to interpret them. So let's talk about interpreting them. We see that this hypothesis test has a power of 0.18 or 18% of rejecting the null which is that the population proportion is 0.5, when the actual population proportion is 0.6. Or in other words, if the true population proportion is 0.6, there's an 18% chance of making the correct conclusion of rejecting that null hypothesis when p is equal to 0.5. So there's a very small difference from 0.5 to 0.6. So what we're saying is, if the population proportion isn't 0.5, but it's 0.6, there's only an 18% chance that we would correctly reject the null here. And we would like to be able to correctly reject the null. We would like that power to be high. In this case, our power is only 18%, and that's not very good. So let's look at what happens if the actual population proportion were 0.7, so that you have a 70% chance of having a girl when you're using this X-sort method. Well, in that case, the power ends up being this 0.436 from the second row in our table. And that means that you have a 43.6% chance of correctly rejecting the null hypothesis when the actual population proportion is 70% as opposed to that 50%. Or in other words, our power increases as the difference between the true population proportion and the claimed population proportion in the null increases. And I think that that makes sense, that as we get farther away from the claimed population proportion in the null hypothesis, we would be much more likely to make the right decision. And that power is talking about making the right decision when the right decision is to reject the null hypothesis. So in general, increasing the difference between the assumed parameter, that's this p-value here, and the assumed parameter value in the null hypothesis, and then the actual parameter value, and that's in this column here, sorry, that's going to result in an increase in power. Notice that if the difference between if the true population proportion is 90%, and we're testing that, we're using this hypothesis of p equals 0.5, we have a 98.8% chance of correctly rejecting the null hypothesis in that case. So as this p-value goes up here, the power of the test goes up over here. Now, we talk about alpha equaling 0.05. That's a common choice for our significance level of the test. And alpha is associated with type 1 error. Now, power is the complement of that type 2 error. A power of at least 80% is a common requirement for determining that a hypothesis test is effective. Some statisticians argue that the power should be higher. When designing an experiment, we might consider how much of a difference between the claimed value of the parameter and its true value is an important amount of difference. We want that difference to be large enough so that we have quite a bit of power. So when designing an experiment, if we have this goal in mind of having a power value of at least 80%, it can be used to determine the minimum required sample size. Now, we're not going to get into that in this class. I just wanted you to be aware of what power is and of the relationship between power and those choices of the population parameter, P, that are actually occurring, and the population parameter that is claimed in the null hypothesis. As the difference goes up, the probability of making the correct decision and correctly rejecting the null also goes up. So if p is equal to 0.5, or if we're saying that p is equal to 0.5 in our null hypothesis, but it's actually equal to 0.6, well, the chances of our hypothesis test getting that right, correctly rejecting the null, is only 18%. But if our true population proportion is 90%, and we're comparing it to 0.5, we're pretty sure we're going to reject that null hypothesis. We have a 98.8% chance of rejecting that null hypothesis. So make sure you understand what power is and how to interpret it. Don't worry about computing it. That's all we need for this course.